What we're going to do in this video is to draw the deformed shape of the beam shown here, without the benefit of having a moment diagram. And in the process, we're going to sketch what the moment diagram, the shear diagram, and the free body diagram should be, given the assumption that we've made about the deformed shape. This is a difficult process. It requires you to think qualitatively to keep deformations, moments, shears, and forces in mind and the relation between them. It's certainly not easy. It's something that requires practice. At the same time, it's very useful because you don't need to do a lengthy calculation to get an answer. It's a way to obtain an answer qualitatively and know what you're doing before doing any calculations. The only stipulation in this problem is that the force P2 be greater than P1. Other than that, we're not using any specific values. This is all qualitative. What I'm going to do here is start with an assumption. And the assumption is that if I push on a point, right here and right here, if I push on a point, that those points are going to move downward. So I'm going to draw in these 2 points. I'm also going to keep in mind my boundary conditions. And I'm going to sketch a smooth curve through these points. Maybe I drew this point a little bit low, so I'll adjust that right about there. I'll sharpen up this deformed shape. But you see that this deformed shape came from a reasonable assumption on the displacement of these 2 points, plus knowledge about the displacement of the points on the support. We know that a pin and a roller don't displace vertically. One thing that we note is that over here the curvature is upward, and over here the curvature is downward. So right about here, I've identified a point of inflection. And what I'm going to do is I'm going to draw a reference line upward to the moment diagram. Why would I do this? Well, I know that at the point of inflection I have 0 moment. So this will help me sketch out the moment diagram and see if the moment diagram is consistent with the applied forces. Maybe this deformed shape isn't viable. Maybe it's wrong. So I need to look a little bit at the moment and shear diagram, the free body diagram, and see if they make sense with the entire scenario. So let me sketch in here. That's my point of 0 moment from the displaced shape. I have points of 0 moment at the ends of the beam. Over the left-hand segment, I have downward curvature. So let me draw in the moment diagram. What shape should the moment diagram be? Well, on the free body diagram, I have no distributed loads, no uniform loads. So 0 uniform load, constant shear, linear moment. So all of my moment diagrams are going to be linear. The only way that I can get from 0 moment to negative curvature with a straight line is by going from the 0 point all the way down to the point of a discontinuity. Then I would come back through the 0 point up to the other point of discontinuity and back down. This would be negative curvature. This would be positive curvature. Is that reasonable? Let's work upward with the shear diagram. Here, if I draw the shear diagram, I'm going to come down a certain distance, P1. It's going to be constant right here. Now, what direction do I go from here? Well, yeah, I'm gonna start again with the reasonable assumption that if my forces are pushing down, my reactions are pushing up. That's not always going to be the case. I'll make that assumption. We'll see if it works out. I'm going to say that this force here is larger than just P1. It's going to carry P1. It's also going to carry a part of P2. So I'm going to say that this force is going to come up to here. And this is going to come down by an amount P2 down to here. and then the force at the end is going to push me upward. So this will be negative shear, positive shear, negative shear. I argued from how plausible the forces on the free body diagram might be, but we can also look downward and recognize that negative shear corresponds to negative slope, positive shear corresponds to positive slope, negative shear corresponds to negative slope. So these are consistent, and the guesstimates that I made about the free body diagram are also consistent with that. So everything I've done here tells a consistent story. As a matter of fact, even this assumption here, P2 greater than P1, well, this distance right here is P1. This distance right here is P2. So if P2 weren't bigger than P1, then the shear diagram and everything else would look different. We'd have to start over. So that's the reason that this assumption here has to be there. But let's get rid of that annotation there. And here we have our finished product. You notice actually that we had the correct answer pretty much right off the bat. I started out by sketching a deformed shape. Then I had to do a lot of work to convince myself that that shape was correct. I back calculated the possible moment diagram that's implied by the shape, and then I went from here and argued about the free body diagram, the shear diagram. Perhaps the easiest way to see this is by looking at the slopes of the shear diagram with the slope of the moment diagram and seeing if those give us, at the end of the day, a free body diagram that can potentially be in equilibrium. Here, there are upward forces to balance downward forces, and there are, say, summing moments about here. These two forces give us a counterclockwise moment. This force gives us a clockwise moment. Again, with the correct values, those can potentially equilibrate. So there's nothing here that is inconsistent. We feel relatively confident that this is an accurate deformed shape for that beam.